Hello, and welcome to Lecture 2 of the Intro to Backend Development course. Today, I'll be talking about databases. So, as a recap from last week, we talked about the client-server model. It's really important because it's the backbone of a lot of applications, and where clients and servers are computers, and it's important to note this medium of exchange between clients and servers, where clients send requests and servers reply with responses. The reason that we have this separation between clients and servers is because we want to abstract away from, building the UI versus managing the data that users interact with. So requests are initiated by the client. They're sent to a specific endpoint at a URL, where the URL contains domain, the route path, and URL parameters. This is optional because you may recall that last lecture we talked about a GET request might needing some additional information from the client so that the server can respond with a meaningful response. And method also indicates the nature of request, so this could be post or get or delete. And the meaningful data is sent in the body of the request. In the case of this class, we use JSON, but do note that there are other mediums of data exchange formats. Could be XML or protobuf, but JSON is just the one that we're using in this course. Now, as for responses, they're triggered by a client request, and they also come with response codes such as 404 or 200 or 201, and they indicate either success or failure. They could indicate whether a client has successfully made a request at all, or if the server was just unable to respond appropriately. It's also in the form of JSON data, just like the request. And here, a client is just making a request to the server, where a route is triggered, which tells the server, hey, I need to be doing something to respond to this request that was just made by the client. And so it will perform that data operation given the route, and it will return a meaningful response back to the client. So one problem that we came across that you might already know from doing the first assignment is data persistence. The issue with our previous implementation of a database is that we used a Python dictionary. We had to manually add in data by using a counter that we incremented ourselves to ensure that we had data that was uniquely added to our database, or quote-unquote database. And the problem with this is that once we stop the server, all of our data is lost. All of that hard work of incrementing all of our IDs and adding data correctly into our Python dictionaries, all of that's lost when the server crashes. And in fact, servers can crash anytime. It's actually inevitable, and this is really bad if all of our data is lost. Another issue is that Python dictionaries are just not good for holding very large data sets. I don't think I'd be able to fit in 1 million users' information into a Python file. Another issue is that people could try to find a way to insert data that's not an expected format. If you recall, when we made post requests, you specified fields that a user could send or a client could send to a server or a backend, but it's not guaranteed that the client will send you a Boolean or string or an integer. And you could essentially end up with a massive data structure, your Python dictionary, that's inconsistent. Whereas a solution for this would be a database. A database could enforce rules like, hey, if you're adding information here, I want you to make sure that it's a string or an integer or a Boolean. But let's talk about what a database is first. It's a collection of organized information. It allows you to interface with the data at an abstract level that makes it easy to access, update, and manage data. It's implemented as a collection of tables. And now, what does that mean? So here's an example of a table. As you can see at the top in the gray, we have column names, ID, name, quantity, and price. These are descriptive names or fields that we want to be able to add as pieces of data. They also specify a data type. You might notice that, IDs are integers, 1, 2, 3. Name data is all strings. Quantity is integers. Price is some decimal value. And here, columns are enforcing some data type, which was not previously seen in our Python dictionaries. Now that we've talked about the columns, how about the rows? The rows are a set of data that fills in each of the column values, and it essentially represents one item or one piece of data in a table. Again, the IDs are unique, similar to our Python dictionaries. However, what's a lot easier for us to use is that the database will automatically increment our IDs. So we don't have to worry about, manually having a counter. Another important thing to note is if we delete data, we don't reuse the IDs that have already been deleted. We actually just add on to it, or the database actually just adds on to it. This is for the sake of time efficiency. It would just be hard for the database to track what's been deleted and what IDs are up for grabs to be added and used. A very important distinction to make is that a database is not a table. A database could have a table, which could, have the confusion that a database is a table, but it's more likely that a database contains multiple tables. And let's see how that makes sense. So in this slide, the example is a little contrived. You have a fruit table and an employee table, but what does that even mean? So I'll give you an example that might be able to clear up your confusion. So let's take the example of Facebook. So Facebook has lots of data. It could be users or it could be games that they offer. So it wouldn't make sense to have one table that mixes in all of the users and the games. You would have two tables, one for users and one for the games. And you would define relationships between the two, like, okay, for these users, they play Tetris or Words with Friends. And for these games, we have these users that are super good at Word Blitz. Of course, this is a silly example, but it shows that you can have different types of data that can be related to each other that are collectively a single database. Now, it's also important to note that IDs are unique per table and not globally in the entire database. This is because later, when you define how you want data to be extracted, you will define what ID specifically you're getting the table from. For example, ID from a fruit table is different from ID from an employee table. Now let's compare this to what we had previously. It's very important, as you can probably tell, to abstract away and interact with all kinds of data regardless of some unique hierarchy you've defined. In other words, having tables like this in a database allows you to manage data with ease and without having to worry about, okay, I have these fields, I'm not sure, I would have to parse this, the data format's all over the place. So in the case of a database, this is a lot more easier, and you're provided with more tools, which I'll explain later, that allow you to interface with this easily. So with that, I'll recap with the benefits of using a database. First of all the data is well structured. The types are well formatted and defined so that you don't have confusion. And in some ways, a database is like a contract between the client and the server, where the client can expect that they have this data and the server can enforce these rules on the data. It's also important that the data scales well. You have millions of users. How can you put that in a Python file? Well, a database can handle that easily. And being able to query data is super important. The database has its own optimizations of when you insert data or delete data, so this makes it very helpful for extremely large data sets. So let's look at an example of how we would check what fruits are in stock in our Python implementation. First, we would have to load our JSON into a Python dictionary or list. We would have to iterate through every fruit in our fruits data, check what the quantity is, and then append this fruit to a response that we would give back to the client. Well, this is a lot easier if we had some language to help us interface with the database. If you notice here, select, from, and where are in all caps. These are keywords, which we'll talk about later. But name is a field, fruit is a table, and quantity is a field that results in a condition. So this one-liner will tell you which fruits are in stock, which is super easy compared to what we had before. So what is this? This is structured query language, which allows us to work with the data in a database and kind of like a coding language. And it's actually better well known as SQL. So what is SQL? It's a language for communicating with databases. It allows you to add data, delete data, get data, whatever you name it. So let's look at the example of creating a table. Here we have two green words in all caps, create table. Do note that when you write this in the language, it won't have pretty colors. We're using this to show you visually what this would look like. But it's important to note that they're in all caps out of readability. SQL keywords can be written in lowercase, but it's good style and out of tradition to write them in uppercase to differentiate between the keywords and the actual data. So right now we're just creating a table with the table name, and we specify the columns, which are the fields, and the data types, which could be integer, text, boolean, date, timestamp. There's a lot of options, but we won't confuse you for now. So here's an example of how you would create a table for users. Do note that I'm naming this table user, even though this table can have multiple rows, each with a user. So you have a table filled with users. Here I'm defining a field ID that's an integer. And by primary key, I'm meaning that this ID is unique. So for every user, I'm going to have a unique identifier, and it will auto increment, which means that every time I add a row to my table, the database will automatically add my ID by 1. Another field is name, as well as age. It just says that the type is text, which is a string essentially, and not null just means that if I'm going to be adding data to this table, it must be the case that I have to fill out these fields. And another field that I'm requiring, or actually not requiring, is email. It will be a type character with a maximum length of 50. So how about inserting data? It's also quite intuitive. So note insert into and values are SQL keywords. At a table, I will be inserting values 1 to blah, 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 blah in the columns 1 to blah, 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 blah. And actually, if you'll be filling in an entire row of a table, aka filling in all of the columns with values, you don't need to specify the columns because it's redundant and SQL will understand what you mean. So you can omit the columns if you insert values into all of them. Here's an example of actually inserting data to a table of users. So at the columns name, age, and email, I want to insert data John, integer 21, and string email. As for retrieving data, it's also quite similar. You have the keyword select and from the table that you want to get the data from. And if you want all of the columns, you can say select star, or this is actually an asterisk, but we usually call it select star. And this will get you all of the data or all of the fields of a specific table that you define. And you can also define on what condition you want this data to be. An example is if I wanted to get all of the users who are 18 and older, I can say select star, which is get me possibly their age, location, school, email, any field that you want from the user table where the condition is satisfied such that their age is older than 18. Now, when you update data, you use the update keyword, and you define which columns that you want to update the values for, and you can also do this on some condition. And here's an actual example. Do note that if you have multiple conditions, you would still only use one instance of where. You would just chain your conditions in that one line. So you could do this with logical operators like and or. Deleting data, you would use keywords delete from. You'd specify the table from which you want to delete and the condition of what you want to delete. So for example, I want to delete user with ID 1. This is how I would do it. All right, well, that concludes the second lecture of the Backend course. Hopefully it was informational, and we'll be looking forward to seeing you guys all in class for demos and questions, and we'll also try to be doing Polo, which is our iClicker replacement. Other than that, see you all on Monday.